Maybe 1 more minute, and then we start.
I think we are almost all done, right? Yes? Yes, also here. Just keeping out. Oh, yeah, yeah.
And we can proceed to check tools for that. We will get to it. So basically what I want you to see here is that the main goal of doing an assembly is to reconstruct the original genome as accurately and as completely as possible. So you start with your reads from the sequencing company, and what you want to do is assemble them, find overlapping parts of those sequences that you can use to build longer and more contiguous sequences called contigs, which gets you closer and closer to having your genome totally assembled. And for that, there are two main approaches. There is a reference-based assembly and a de novo assembly. So the reference-based assembly uses a reference genome, like the name says, to guide the assembly process. And then the raw sequencing reads are aligned to the reference genome, and then the gaps are filled with those reads that did not align to the reference. But I believe Victor said before, answering to somebody, that this approach is a very luxurious one because most people simply don't have a reference for it. So the most widely used approach would be de novo assembly. So you start from scratch, no reference at all, and then your raw sequencing reads will be assembled into contigs without using this reference. And it is very commonly used for species that come from complex environments like soil or gut. and that have no reference genome. So that is the one that we will focus on today, because it's the most widely used, it's the most common scenario to have this one. So Victor already talked about the brown graphs. Those are used for this. When you have no reference, you have no starting point, so you need some kind of algorithm to detangle, let's say, the structure of that genome. And then one of these, which is a very good one and we use a lot, is SPADES, that was mentioned before today. Now, this is the paper when where they talk about SPADES, and this is a basic command line that you can use to run SPADES. I have in here, this is Linux, so don't attempt to run this in our studio because it will not work. You need a Linux server to do this. And then this is the very, very most basic way in which you can run SPADES. So you call the program and then you say, what is the directory or the folder where I want to store my assembly? And then since we have the paired end reads, forward and reverse, then over here, we put all the reads that are forward, all the ones that are reverse, and it's done. And in some hours, hopefully, you will have your genome assembly. And it will look something like this. I hope you can all see. But basically, you have this file, which has a header and a sequence. Do you know what type of file that is? It's a FASTA. FASTQ is a FASTA with quality. This one has no quality, just the sequence. So header and sequence, that is FASTA. And then SPADES is very nice because it not only names the contigs, but also shows you the length of the contig that you got, and then the number of reads that were used to assemble that contig, or to build that contig better. But this is a very challenging task, and Victor touched upon this a little bit. So there are repetitive sequences. That's why new algorithms have been developed. There can be sequencing errors that interfere with this process. And depending on the sequencing technology that we use, well, we have to keep that in mind to choose the software that we have. So depending on if it's long read sequencing or short read sequencing. But luckily, hopefully, I think it's luckily, for this challenging task, so you don't have to worry, we have many, many ways to address that. These are some options of assemblers. Victor showed others, and there are more. We're missing some others. And I think, yeah, SPADES is not even here, so there are a lot of them. And over here, you can see some resources to look into them. You already know GitHub, and as you can see, most of them are on GitHub because this is very widely used, as we discussed on the first day. So we really like SPADES, so I don't think it's necessary that you go through all of them, but each of them has its weaknesses and strengths. And if you're very, very interested in the assembly process, then yes, please read about them, but SPADES is very, very nice. So that's the one I mostly use and the one I have the most experience with. And then, when we already have chosen the tool and we already did the assembly, we can check the quality of the assembly. And for this, there are two very important characteristics. So we should check the contiguity of it, how many gaps I have, the less, the better, and how complete it is. So how many of the core genes that it should have, my assembly actually has. So for these two things, we're gonna see two different software, Quast and CheckM. Over here, I have the very basic way of running them, also in Linux. So you need a Linux server for this. And then the main metrics to measure these things for contiguity are N50 and L50, which we will explain in the next slide. And then for completeness, the number of conserved single copy genes present, which are housekeeping genes that are distributed throughout the whole genome, and that should be found in your assembly if the genome is complete. Yes, I will continue then. So M50 and L50 is a measure of contiguity, and you will see why. So let's say that this is my genome right here. These are all the contigs that I was able to obtain from my assembly, and this is the total length of that. So if you assort them in a way that goes from your longest contig to your smallest contig, N50 would be the length of the shortest contig at which you reach the 50%, because this is N50, 50% of your total length. So if my total length is 390, then 50% of that is 195. And if I start with my longest contigs, then I see that over here, with this one, I already reached the 50%. And so, since this contig's length is 60, my N50 would be 60. And then L50 is simply the number of contigs that were necessary to reach that amount, that N50. So 1, 2, 3. My L50 is 3. Is this clear, or do you have any questions? Clear then. Thumbs up? Okay, many thumbs, great. So this we can check with Quast, and if you would like right now to go to the Google Drive, what you already downloaded, there is a folder called Assembly Reports. There is one called Quast. So if you want, you can open it. I will assume you are all done because, well, you're very fast. So what you can see in Quast is 3 main results. So one of them is the statistics results, which is in the main page.
When you open the Quast folder, there is one file called report. Do double click in that.
Yes, it's a report. The rest of the files that are there are just resources that the HTML will use so that you can move interactively around it, because you can click on things, put your cursor on things. So the rest in that folder you don't need to touch, just the report.
So that's the report that you get when you run a genome in Quast to determine the quality of your genome. How complete is your genome? Okay?
Double click and it will open in the interface explorer. Yes. HTML. So then you double click and
Okay, I think we're all there. So the main 3 results that I want you to look at, you can play around with the report later if you want. There are many things to check. But the main 3 things would be the statistics, that is in the top on the first page. Then there is a cumulative length plot over there. And if you click on the Icarus viewer, it would show you a context size viewer like this. But then what I really want you to focus on is on the vital metrics to check the quality of the genome assembly. And that you can already found in the statistics table. But the plots are useful to see it in a more visual way, but all the information is already here. So I used a genome of Microbacterium asiaticum, and I have all of this information. But then these are the most important things that you should check right away when you do your quest. So first, the total length. How long is my genome? And then in my case, since I already know it's a Mycobacterium asiaticum, I could just go and Google how long should be that genome and see if hopefully it looks like this. That would mean that I'm close to it. And if you don't know, it's okay to not have the reference. Then your largest contig also, and see how it relates to this one. So in my case, one contig covers 40% of the assembly. So it means I have the first 40% of my genome has no gaps and is completely contiguous. That sounds very nice. And then we have the N50 and L50, which we already explained. It is also very common to find it with 90. And those would be the most important ones. But of course, you can check other things, how many contigs surpass certain length, and all of this. But then N50 and L50 that we explained already, the golden rule is N50 should be as high as possible, and L50 should be as low as possible. Because that would mean I have only a few contigs that are covering a lot of my genome, and that they're very long. So that would be the perfect scenario. As high as possible, M50, and as low as possible, L50. Any questions about that? Yes?
The QC percentage is 66%.
Can you? With the microphone?
Sorry, that is a GC percent.
Yes? Yeah, you can check the GC percentage because this also tells you sometimes about the identity of your bacterium. So if you don't know which one it is, that helps.
But the total length when we are checking for microbacterium, you can also see for the GC percent.
Yes.
That will tell how close it is to the actual microbacterium.
Yeah, you can check all of those. Since we have the reference, that would be ideal. Yes. Any other questions?
Ma'am, is there any specific least, like minimum and 50 value?
Well, the least that you can have is 1. So that would mean 1 contig covers all your genome and you have no gaps. So that is the minimum you can have. It's weird to see it.
That's
but,
in theory.
Yeah.
What can be the maximum L50 value that can be considered as a good assembly?
Well, that depends on the length of your genome. Yes. Okay.
L50 with 1.
Yeah, that would be the perfect scenario. Yeah.
But also it depends a lot on how many contigs in total you have. So, for example, imagine that you have a huge contig, yeah, almost the whole genome, and then 200 small contigs. So, almost the whole genome will be in that one contig, and those 200 small contigs could be a plasmid that maybe you don't care about. She's asking if those small contigs will have a value. Yes, of course. If not, they will continue their activity. But always, as yesterday we said, it depends on your research question. So, do you need a complete genome to answer your question, or can you answer your question, your research question, with a lab genome?
Okay.
More questions?
Yeah, more than thinking like a cutoff here, you need to think that you have your genome, you sequence it, and you are checking the quality of your gene. So then, if you see that you have, for example, higher values on L50 and lower values
Okay, then I will continue with the next one. So that was contiguity, and then we come to completeness. And now also in your folder, in assembly reports, there is one file that is called checkm, I believe, or checkm output. It's one CSV file, and it's only one table. So let's open that one and let me know when you're done.
I think it's CSV, it's comma separated. So what you have to do, you select the first column, the A column completely. So you go to the, maybe you can
No,
show.
Victor, maybe if it's, the format doesn't fit, you can just open it in Google Drive with its visualizer.
Yeah, it's not gonna be difficult. Yeah, showing the screen.
Yeah, but if you just come in here, assembly reports, and do like this, double click, it will show it with all the columns. And this is it. That is how big the table is. Does it work if you do it like this? Okay, great. Then maybe we do it like this. Okay, I think we're all there. So I will continue. Checkm is great for checking the completeness of your genome. So as Victor said before, there are some housekeeping genes that are single copy, and they are distributed throughout the genome. So checkm uses those housekeeping genes, or a set of those, to evaluate the completeness. So what you have right now is a table like this. I gave it some color for the explanation. So checkm is ideal for when you have multiple assemblies. So here I not only have my Mycobacterium, but I have 10 more genomes. And checkm has 43 genes used as markers for this completeness metric. And they should be present only one time because they are a single copy. So this first row has the ideal results in the most important two columns, which are completeness and contamination. A completeness of 100% because it has all the gene markers that it should have, and 0% contamination because they're all present one time. Now, there are some thresholds for what you can consider high quality or good quality. I hope you can see that even from the back. So we can consider high quality, a genome that has less than 5% contamination and more than 95% completeness, like these two genomes in green over here. So this one didn't have 3 of those markers. That's why it's less complete, but it's still not contaminated because the ones that it has, it's a single copy. And then this one actually has 1 more because it has all the gene markers, but the software found 1 extra that shouldn't be there. So there is some contamination, but it can still be considered high quality. And then good quality ones are between 5 and 10% in contamination and 90 to 95% in completeness, like these two. Is that clear? Do you understand why this is completeness? Yeah? Thumbs up? Okay, very good.
This tool is quite widely used, especially for metagenomics. When you from metagenomes, you extract genomes. Remember, metagenomics, you sequence everything that is in that particular environment using shotgun. So then now on Monday, I think, we will look at how do we do the binning. It's called binning. That is the reconstruction of metagenome assembled genomes. Okay? And then you can see exactly how complete are those genomes, how much contamination do they have, and now we will continue with other parameters.
Well, so this was completeness as well. So let's remember we have contiguity, M50 and L50. We understood how that works and why it makes sense that they use that metric. And for completeness, we have the markers, so completeness and contamination. So once you have evaluated the quality of your genome, and hopefully your conclusion is my genome is very good, then you can even visualize your genome and generate a very nice picture like this one. These three that I list in here are some options for visualizing your genome in this circular way. I'm sure there are more. So in this paper, for example, they were reconstructing the genome of Pseudomonas fluorescens, a specific strain. And what they did was assemble the genome. Here we have the length of the whole genome in base pairs. And all these bars in different rings are annotations with the metabolism information. So what kind of metabolism, carbohydrate or secondary metabolites, coding sequences, a lot of things. So this annotation things we can do right after, but the basis for that is having a genome assembled and hopefully with a good quality. And so now that you have your genome, what you would like to know, or what I would like to know is my genome, where does it fall in the tree of life? Is it similar to other bacteria? What kind of relations they have? Is it actually related to them? And that's when phylogeny comes in. But before we go to that, are there any questions? Okay, I think it was very clear. So Guillermo will now explain phylogeny to you. Thanks.
What that we can do on the best one to get the best quality. Because in a stage sequence we can compromise the beta sequence. But in case of Rodino, we need a good quality sequence. Okay. Yes.
It's not sequencing for good assembly.
You're asking for the best of the sequencing. Well, it depends a lot, but I think around 80, 100, it should be okay for the node. Yeah?
Okay, so now we are going to move to the next step, that is phylogeny. So as Luisa explained before, you got your reads, you assemble your genome, you check the quality, you have a really nice quality. So now it's time to learn a bit more of that assembly or that genome that you just assembled. So how can I make a phylogenetic tree? So as Victor explained, there are several methods. So basically in a phylogenetic tree, you build it comparing organisms. So nowadays, you compare DNA. So are sequence-based trees. And you do it comparing DNA. So, but okay, what do you compare? Because the DNA you have a lot of DNA in your bacteria. So what you compare? So as you know, this nice tree of life, they compare a lot of microorganisms and eukaryotes, but comparing the 16S ribosomal gene among them. So this is based only in that gene, comparing the gene between organisms. Then you can also use housekeeping genes. That's as Victor and Luisa also remarked. Housekeeping genes are genes that you find them widely distributed among the tree of life, and they are constitutive genes, which means that they are normally always expressed and they are essential for cellular functions. As you can think, would you say that the 16S is a housekeeping gene? Well, yes, you find it widely distributed and is essential for like a cellular function. Then you can also perform this comparison to make the phylogenetic tree with the whole genome alignment. So this is more computational expensive, and there are tools there. One is MASH. Victor told about it a bit. We're not gonna say the much, but the question is like, do you need to compare the whole genome of one bacteria to another to get the information that you want? In most of the case, no. And also performing a whole genome alignment will end in a lot of more computational power. So now we move on and we see, okay, for inferring phylogeny to generate a phylogenetic tree, we need to perform two mainly steps. We have our genes, so we are comparing DNA. So we need to, as Victor said in the lecture, we need to align them first. So imagine that we, as Luisa said, we got reads from 3 different genomes. We have our 3 different genomes. Here we have it in this, we visualize it in these nice genome viewers that Luisa said. And then we extract the DNA and we align them. So first we perform the alignment. So we align DNA of all of them, of all the different organisms. And once we got the alignment, using the output of the alignment, we generate a phylogenetic tree. So for each of these steps, there are a lot of tools. So for example, for the alignment step, you have tools like clustal-W, muscle, MAFT, clustal T-coffee, and a lot more. Then for like the phylogenetic inference, you also have a lot of different tools. You have some of the most famous tools that you can find are FastTree, IQ3, RaxML, and Mega. So you have a lot of tools here, and you will think, okay, how I choose one? How I know which one is the best one? That's a difficult question, and it depends on your objective. So imagine that you are comparing only 3 organisms. That's not many of them. So you are only going to align 3 sections of DNA. So there are some tools that are more accurate than others, but also that are more computational expensive. So in the case that you only have 3 genomes, you will go for the most accurate ones, although it takes more time. But now, in the NGS times, next generation sequencing times, sometimes you want to perform a phylogeny that is in the order of thousands of organisms. So performing the alignment with thousands of organisms could take really, really long time. So then you will choose more, still not that maybe super accurate tool, but that is gonna go really fast, and at least you're gonna have your alignment, let's say in 1 week, will be a good result. While if you use maybe one of the most accurate tools, it will end in months running the alignment. And we don't want to wait for months for the alignment. Then with the phylogenetic inference, it's the same. You get the result of your alignment, and you run it to the phylogenetic inference step to generate a phylogenetic tree. So here is the same. Some tools, like as you can see in the name, some of them they're even telling you in the name, fast tree. I'm making you a tree really fast. So if you have a lot of organisms, you will go for this one. But maybe other ones, for example, as RAX-ML, are the most accurate ones. So then if you want to make a small but really accurate tree, you will choose this one instead of fast tree. Sometimes you can even combine them. So the first step, you can do it with fast tree, and then make it more accurate and refine it with other tools. But yeah, from here I want you to have clear that this is the two main steps that you have in a phylogenetic inference workflow. So now I'm going to tell you about a tool called Barnab. So imagine that you have your genome, but okay, you open your genome, imagine in your notebook, and you have these lines of nucleotides, a lot of lines of nucleotides. So it's not easy to find the 16S gene there. So imagine that you want to do phylogeny based in the 16S gene. With this tool, Barnab, and here you can see an example of how to run it also in a Linux server. With your assembly, you can run just this command, Barnab, quiet, so it keep it quiet and fast, and your assembly. And then the output that you will get is like this. So anyone can tell me what is this output? A FASTA file, really good, because we have our arrows and our sequences. So as you can see, it not only gives you the 16S gene. Here we can see that from our example genome, that I call it genome 1, it got us the 5S, also ribosomal unit. Also, it got us the 23S. And also, it got us the 16S regions. So then, with this program, really easily, you can extract the 16S or other ribosomal unit sequences to then move on to the alignment and other steps. So, but yeah, sometimes you've seen these steps, but okay, I'm not like a bioinformatician, I want to go to the easy, a quick option, but still a good one. So there are plenty of tools that performs the whole phylogenetic analysis all in one. So the only input that you have to give is your assembled genome. So imagine that you did everything as Luisa said, you got your genome, you have your genome in a file, so then you just want to sometimes throw your genome through a pipeline, and that the pipeline just gonna return you a phylogenetic tree. So some of these ones, Victor already talked about them. You have Amphora2, which performs the whole phylogenetic analysis based in a database of 139 housekeeping genes. Then you have Phyloflan3, that is one of the ones that we like the most, and it has more than 400 marker genes to do your phylogenetic analysis. So imagine what is going to be more accurate. You are performing your phylogeny inference only with the 16S, or using a tool of this one with more than 400 genes together. Of course, using more genes will yield to the more realistic result, and only will be more accurate. And then you have also this one more modern called AutoMLST. This one, if you just have one genome, this one could be interesting for you, and I recommend you to check because it has an option where you can they have a pre-generated tree, so you can load your genome and it will map your genome to the already pre-generated tree, and it will tell you in their tree which bacteria is the closest to your bacteria. So it's really nice when you have only one genome. Well, I'll talk about autolog genes, but this is like housekeeping genes, but I will talk more about that tomorrow. So I'm gonna get more in deep about Phyloflan3. Why?
because it's the one that we use the most, the one that we trust the most. So here you can see, and all of you are already experts and know GitHub. So if you go to this GitHub, you can get explanations. You will get explanations of how to install, how to run the software. You also need to run it in Linux server. But I'm going to show you a bit more in detail like how to run it. Okay, so we want to run the file of LAN in our genomes. So this is the command that we are running in Linux. So we have file of LAN, is the name of the program. We have -e input folder. So input folder will be a folder that we have with all the genomes that we want to have in the phylogenetic tree. Then we have database. So what means this? Well, this is one of the strengths of file of LAN. File of LAN is that flexible that allows you to choose different databases of markers or housekeeping genes to perform the phylogeny. So you remember, for example, amphora2 that we mentioned before, all that list of markers is also included within file of LAN. So you can choose 400 genes that file of LAN has, or even choose other databases of different markers. Then also, so it's the database parameter. So if you place here amphora2, it will work with amphora2 markers. Then it has these other parameters that file of LAN also adapt the algorithm to the diversity of your analysis. So imagine that you are building a phylogenetic tree of everything the same species. Then, which diversity will you choose here? You will choose low diversity. Why? Because all the genomes that you have are the same species. Then if you have, for example, all the genomes from the same genera, so from the same genus, sorry, then you will choose medium. And imagine that you have genomes from different organisms, from different phylum or even kingdom. Then you will choose high diversity. And then the algorithm of file of LAN will automatically adapt to the diversity that you want to see. And that's a really nice thing that other software don't have. Then also, you have the configuration file here with this F and the configuration file. So here, you see before that for each step of the phylogenetic inference, the alignment and the phylogenetic tree inference, you have multiple programs and softwares, right? Some of them will work better in one condition, depending on the amount of data you have. Others will work worse. So one of the also strengths of file of LAN is that you can check and make a configuration file specifying which software you want to use in each step. And that's great. I can tell you that that's great and can save you a lot of time. So this is the three main reasons that, for example, we in our groups, we like to work with file of LAN 3 to create phylogeny. So one, because it's everything in one, so you just need to put the genomes in one folder, and two, it's really flexible and you can modify and choose different tools for your for different analysis. So now, okay, we run the genomes. We have file of LAN 3, so it will give us an output as a tree. So let's imagine this condition, this scenario. So imagine that we were working, we were isolating genomes, and we isolated this genome, and then you show this genome to your supervisor, and your supervisor tells you, ooh, this genome, this bacteria, sorry, this isolate, I'm sure it's a Burkholderia. I'm completely sure, but not about the species. So you are like, okay, it's nice to know that it's a Burkholderia, but I want to know also the species. So you do the assembly, as Luisa said, all the steps, you check the quality of your assembly, you have a good quality genome. So what you do next? Then you can go to the database and say like, okay, I'm gonna download, let's say 7 known Burkholderia species from the NCBI database, okay? And I will see which of these species is closer to my isolate, or if or I want to see also if my isolate is really a weird species compared to these 7 ones. So you just take all these 8 genes, in total 7 plus, or isolate, and you run them through phylophlan. And then you will get a tree file that we want to visualize. And for visualization, we always use ITOL. So ITOL is a really nice software that we're going to use a bit now to visualize phylogenetic trees. So now, if you go to the files that we download, there is a folder called phylogeny, and you will find this file inside. Okay? So now I'm going to do it with you in my laptop. We go to Google. Here, we open a new tab, and we are going to type ITOL. Okay? Wait, I have it already there, but I'm just going to type ITOL. If I have internet, I think yes. Not that good.
Are you connected?
Yeah, it's connected, but no, not loading. Oh,
Is there any way that we can get internet connection?
now it is connected. Oh, perfect. We are back. So if you went to Google ITOL and then you click the first link that you see, you will come to a website like this, okay? Are you all in there? Perfect. So now this is really easy. That's why we like it a lot. You go to the tab here, upload, and just press it. And then it shows a new page. So now what you are going to do, you're going to open, well, you're going to take your, well, let me go here. So you're just going to drag the 5 phylogenetic tree Burkholderia.tree that was inside the phylogeny folder, and you're just going to drag it to the web browser. Ah.
Okay, I think some of you already got it there before Guillermo. So who has problems?
Okay. Is everyone good? Can everyone see this? Good? Thumbs up, everyone? Okay, nice. So what we see here is the tree that we created. So we are visualizing the tree that we created with phylophlan 3. So we have, as you remember, we had one bacteria that we knew is a Burkholderia, but we don't know the species, and then we put 7 other Burkholderias that we know the species. So the Burkholderia that we don't know the species, we call it Burkholderia sp. So we have it here. So then which one is potentially the species of our Burkholderia sp, looking to the tree? Great. So now we know the potential species. It could be that it's not the same species, of course. We cannot just say that it's the same species. But we know now that of the 7 bacteria, the 7 genomes that we downloaded, the closest to our isolate is Burkholderia gladioli. So that already is telling you a lot. Well, this is a really simple example of what can you do with ITOL. But this is a really powerful, really flexible, and it allows you to make really, really nice trees for publications too. So I encourage all of you to maybe play around, and you also have a lot of documentation here. If you go to the help tab, you can go to help pages, and you have a really extend documentation that could help you to add things to your tree or modify and visualize in different ways your tree. They are so nice in ITOL, they're so nice that you even have video tutorials. And who doesn't love a video tutorial? Yes? Yes, of course. So you can see in the above that there is a tab called Help, right? So this is some documentation that you have to make to help you decorate and visualize your phylogenetic tree. So you have help pages where you have more a document with different steps, different things that you can add, how to decorate it, but also you have video tutorials. Well, I lost the internet again. But well, I encourage all of you to play around there because it's really nice.
So if you see on the right side, when you load the phylogenetic tree, you can modify all the characteristics of your tree. You can increase the size of the text. You can also increase the size of the branches. You can play around with it. And I think it's quite, you know, no?
Yes.
Yeah, and also if you go to the help page, you can add different rings. You can add bar plots if you want to your phylogenetic tree.
No, I'm good. No, I don't need the but I don't need the internet anymore, so I'm good. Don't worry. So, okay, I will connect it. Okay.
Because yeah, you can build up their phylogenetic tree with all kinds of information about the point.
So you can even see visualize it in different shapes. Like here, for example, it says circular. We are now in rectangular, so we are seeing like this. So you can click in unrooted, circular, just explore around. And well, this tool, as I say, I encourage all of you to explore it and see what can you do. And if you have a phylogenetic tree, it's also really nice. If you have also really huge phylogenetic trees, it's really nice to annotate them. So now I want to show you an example. So I'm going to go back to the presentation. Okay, we saw this. So I want to show you an example, for example, of a phylogenetic tree that I made. So you can see how beautiful these phylogenetic trees can end. So this, I just download all the Burkholderia genomes available in the database, and I create a phylogenetic tree with phylophlan, and then I got the output, and like the one that we have, and I load it in ITOL. So you see, I annotated with 3 different rings. This first one ring from inside to outside is lifestyles. That we say, okay, these ones are more environmental bacteria, the ones that are purple. Then we have this orange-red, more opportunistic plant pathogens. We have in green plant pathogens, and in gray we have the ones that we didn't know. So you can see how in the tree, they are kind of clustering together with the same lifestyle. Then I also add another ring with some of the most common species that are in the Burkhold area. So you can see in different colors the species. And then in the last ring, I add a bars that indicate how many genes involved in the metabolism of carbohydrates are in every genome of the tree. So you can see how it changes depending in regions. Some of them is linked to the species too. So this is just an example of how using ITIL, that is click-based, is really easy to use, has a lot of documentation, you can create really, really nice phylogenetic trees. So I encourage you to play around. That's how you learn to do it. Just play around, you click in everything, see what happens, and yes.
Thank you, Guillermo. I would like to go back to the help page. So as you saw, you have a video tutorial as well. So that's always nice to have it. But I think in the help page, you can scroll down and you can see that there are already quite a lot of, but there is a lot of information that you have to read and so on. But the most important, let's see if I read it,
There, you have
is, for example, no, not this one, room neither. Tree annotation. So this is how you make the rings around the phylogenetic tree, how you add the box plots or the bar plots, or you can add heat maps and so on. And if I go a bit down, you can see that in every function that is given this program, you have an example file. Okay? So if you open that example file, is it gonna open? Yeah. So you have here all the requirements for the generation. Okay? So you have the separator, you have the label, you have the colors, so you really can modify everything and make it as better you like. So, and then here, for example, is where you have to put the metadata, so the name of your bacteria, the name that you, the same name that you have it in the phylogenetic tree, and then the characteristics that you want to add. So for every circle or every ring that you want to add, you need to do a separate file. Okay? But again, it's something that please have a look, explore, read about it, and also maybe it's good to see the video tutorial. Okay, questions?
One of the most important practicals, and you all will be using this tool in your thesis project. I'm sure a lot of doubts must be there. You might be using some other program.
Using other programs for phylogeny?
At least you can
Mega.
comparison of these two and ask what is the advantage of this tool over the other tool what you are using right now.
So you can also take the phylogenetic tree produced by Mega and load it here and decorate, because I don't know if Mega allows you to decorate. No. Yes? Okay. Okay. So then maybe an idea for you it will be to generate your phylogenetic trees with Mega.
Limit. Yeah, for me, I don't use it because if you put more than 100, 200 bacteria,
Okay, I
Mega 11, not that.
You also use it Mega 3.
It's
right?
11, yeah.
Yeah, of course. Now it's no, but then what you can do, you can export to NetWeek and then put it in the drag it in the icon, and then you can start decorating as you like more. You can have quite a lot of options. Believe me, it will change your life. Yeah, just use Mega 1. Mega -1, I think. More questions?
I expected a lot more questions on this molecular biology. So different kind of genetic algorithms are there. You have a UPGMA, neighbor joining, maximum likelihood, minimum evolution, Bayesian. Oh, something I expected from all of you.
Something that it will be interesting for next stage is also the tool that Guillermo mentioned at the beginning, BARNAP.
Barnab? Mm-hmm.
So that tool is quite used in metagenomes as well. So you have your metagenome, and then you can run BARNAP to extract the 60ness from your metagenome. So basically you have two for the price of one. You get the taxonomic composition, so the 60ness, plus the function.
Nice.
Yeah? So, but we will go through it on Monday.
How many of you know this I told before? Yeah, there is one guy. Yeah.
So you know how to do track the files, how to build the files, and so on. Nice. That's great.
Yeah. So that is 1 in 30. Yeah.
Yeah. Yeah. No, two. You as well. Yeah.
That's great. Very nice. Okay. Shano must be using quite a lot of Mega, right?
Yes, sir, I do.
Then you can share what is the advantage this is offering over Mega.
Actually, sir, in Mega, we cannot do that much of editing. We need color, font size, plus it is way too slower. It will take so much time for so many genome sequences if we are doing altogether alignment. It takes much more time. I feel that.
And you, so I think Mega you can only do genes, right? Not full genomes as well. Wow, that's amazing. I didn't know. Because when with Mega 3, yeah, it was only the genes.
Yeah.
Yeah.
I generally use Mega X. New versions are also available now, so through that you can do that.
So now my question is, so I think Mega is an amazing tool. You can keep using it if it's working for you for the amount of data that you have. But my question is, are you willing to use this tool, for example, after Mega? So you generate your trees with Mega, and then you decorate and make a beautiful tree using Python. That would be a good option for you, right?
Yeah, but the function is something which is very unique here. The Mega cannot offer that.
Extra options they have.
Yeah. See, this lifestyle prediction or lifestyle determination is very important for all of us. So that's something very, very nice. I think it's an excellent program. I think all of you should really practice it. Okay. Any assignments for them to use this tool? You're telling this one?
I think I would say, make a phylogenetic tree as beautiful as you can. Try to, modify the trees that are in the manual or even the tree that Guillermo provided. or yeah, maybe even Guillermo could provide more trees if you are interested. Guillermo could provide the tree
Yeah.
that he showed with the example files. Or, yeah, then,
One comment that I would say, like, I also used to use Mega, and it's really nice. But when you are working with, for example, the whole Burkholderia genus, you are working with thousands and thousands of bacteria. So in Mega, I always had problems to have trees of maybe of more than 100 bacteria. While with ITOL, I was able to generate trees of even 15,000 bacteria.
Yeah, maybe from the student's point of view, suppose the different genomes are having different values. No genomes
Yes.
are having the same value. What I call size normalization. How those gaps and missing
It's good.
So
I
in
only
the
have one.
alignment is the alignment is not done by ITOL. So the alignment ITOL is just for visualization.
Yes.
So you can only look at the result of a program already pre-computed the data. So, but Bioplan, for example, is dealing with that, and what Bioplan is doing, even though everything is wrong, but what it does is that well, give us a your 100, 200 genomes. They have different sizes. They are draft genomes, whatever. Yeah, and then what Phyloplan does, and Fora as well, is map, is search for the housekeeping genes. And the ones that are found, maybe you have 400 in the database, but it only found 20. So those 20 that are the same size will be aligned and will be used for the phylogeny.
This is clear to all of you?
So
This is
then,
a very important point.
and another thing is that I don't know how you are doing the trees in Mega. Are you using 16S or are you using housekeeping genes? Okay, so how do you concatenate the housekeeping genes? Manually. Okay, that's time consuming. So what this tool is doing automatically. But even though for that there are options, if you want to continue using Mega, you could use other tools that are available to concatenate your genes based on the ID. Now I can give you some reference because I have been there and it's very annoying to concatenate one gene after the other.
Manually, very
Manually,
challenging.
and you can make mistakes. Yeah, that's very important.
All those things have gone now. You can go directly with this program.
One additional.
Yeah, this is clear to all of you. The Mega versus the iTool. There it is manual. Here it is automatic.
Yeah, one addition about this Phyloplan tree, as you say now, you are concatenating manually. So at the end, you are going to end with you're going to end with a really long alignment. So one of the most important steps also that is not in Phyloplan tree is that when you have that big alignment, it only takes some of the most important positions in the alignment, reducing to 80%, reducing 80% the size of the alignment, making that when you are inferring the phylogeny will be way more faster.
Instead of taking the whole gene that has information that is not needed for the phylogeny, it takes automatically maybe the domain of that gene instead of the, and then you reduce to maybe each gene will be 30 amino acids. So then you end up with an alignment of, I don't know, maybe 2,000 positions. Yes. There was a question here.
Sir, can we just try to find, like, for example, I don't have the answer sequencing, but I have around 1,500 bacterial sequences, bacterial sequences. So, like those contigs I
if I understand well your question, you have 16S gene, yeah? The 16S gene, just that, the 16S. No, I don't think that you can use it with pyroflam. Or you have whole genome. Whole genome.
For 16S, you have different kind of.
Like we can separate out, sir, as sir told, we can separate out all the 16S sequences from like the whole genome, and we can use only those 16S sequences in pyroflam, right?
No. No. Huh? If you are getting the 16S genes, I would go manually, not manually, okay? I would take an alignment. I will do the alignment with muscle or wherever, and then run a fast tree. Fast tree, if you are very interested in the, well, yeah, Raxenel will be extremely slow if you have really high number of samples, but you could also run it. But if you have draft genomes, okay, so genomes that are not complete, my recommendation would be to put it in phylophlam, input in phylophlam, and let's see what it finds. So maybe it will find 10 genes that are among all your drafts, and then you can infer better the phylogeny that with only one single gene that is 16S.
And also one issue. So for example, I already have an alignment, and I just want to do the tree from the alignment. So you can indicate to the program that you just want, that you are giving the alignment, and they are just need to generate the tree. Or even if you have also the sequences. So for example, for you have the sequence, you can say like, hey, I have already my sequences, so I just need you to do the alignment and the tree, but not to find me the sequences. So it's really flexible, and there is plenty of documentation to do things like that.
Okay, any more?
What? Maybe a lot.
Yeah, exactly.
Maybe a last detail of today to close the day. Next week we have the literature discussions. You remember? Every group has been assigned one research paper, again to expand the theoretical knowledge, and secondly to see what kind of methods and tools that they use that we have discussed this week. And also, I think one part is also to present, to catch the most important elements of a paper and present this. And that's why, the time is well, limited is not a good word. It's 15 minutes. So today I got a few questions like, Jos, but can we, present? And, oh yeah, we have 20 minutes. You don't have 20 minutes. You have 15 minutes to present. So 15 minutes is 15 slides. And then there was also a question, does one person from the group need to present it or multiple persons? You can divide the task. So one person can give the introduction, a second person basically, another part. So again, I put the contents of the presentations here with just an indication of the time. So keep a brief intro with the context and the research question and a hypothesis, 3 minutes. Then a bit more time on the methodology, because this course was also, of course, focused on a number of tools and methodologies in microbiome research. Then the major results, conclusions, and novelty. That is always important to pick out, what is really novel in this paper. And then bring up a few points for discussion, right? And then, so after 15 minutes, when you give the presentation, you will hear an alarm, and then you need to stop, right? Good, and then we have 5 minutes with the whole group to discuss the paper, to, probably some questions come up. And I'm sure you're going to be able to, bring out the message of the paper in 15 minutes. Okay? Good. So that was again, start early with reading the paper. Don't underestimate it. Some of them are quite tough. It's okay if you're not going to go all the way through all the supplementary information. There are some papers which we gave you, and I think if you would print all the supplementary information, you will get to about 100 pages. So focus on the core of the paper, the novelty, right? And then discuss, the three of you, how to present the topic. Okay? You're gonna be fine to do that.
I think you have a task to carry out now. Start working on those presentations right away, if you have not already started.
That was a great day.
Yeah, excellent.
Thank you.
So maybe a good exercise. So if you have already a phylogenetic tree about your favorite bug, your favorite bacteria, your best phylogenetic tree, so you could tomorrow maybe bring your phylogenetic tree plus the metadata, whatever you would like to annotate in your tree. So this bacteria X is antagonistic against Fusarium. This other one is antagonistic against Pythium. This other one is antagonistic against Rhizoctonia. Yeah? And then we can try to help you to plot it in
Hold it common.
iPhone. Okay? Would that be an idea? Good.
Okay, so very briefly, especially for our online viewers, I would like to summarize a little bit more about what we did this afternoon. So on my side, we talked about the assembly of genomes, what things to consider when you're assembling your genome, and the fact that you can choose from many assemblers to do that. Then there are some metrics and parameters that you have to keep in mind when you check the quality of your genome once it's assembled, the contiguity and the completeness of it, and there are specific metrics for that, M50, L50, and then the amount of core genes that are single copy and are present there. We checked, we went through the reports that these tools give out, and then we also explained how these metrics make sense and why they are a good indicator of high quality in your genome. And then phylogeny.
And in the section of phylogeny, we learn how to after assemble the genomes, how to which ones are the most important steps in phylogeny. We have two. We have the alignment, and we have the inference of the phylogenetic tree. We saw that we have plenty of different methods, so it's really difficult to choose the best ones, but there are already tools out there that compile all these methods and automate the whole workflow. And also we learn different tools to visualize large phylogenetic trees and annotate them with our metadata of interest. And thank you everyone. I will see you tomorrow.